Take a look at problem number 2. And remember, this is a kinetic energy problem. And if it's a kinetic energy problem, it's an energy problem. Okay, so the thing we have to remember about energy problems in general is total energy at the beginning is equal to total energy at the end. Okay, those things are equal. Remember, your total energy could be potential, could be kinetic, could be work, and now we're adding in rotational kinetic energy, okay? Any one of these things, total energy could be made up of those 4 things, okay? So at the beginning in problem 2, what you have is a guy running, okay? So a guy has mass, and he has a speed, so which kind of energy does he have? Well, he's on flat ground, so he doesn't have potential, okay? He's not actually moving anything, so he's not doing work, and he's not spinning, so he doesn't have rotational kinetic energy. What he has is just straight up kinetic energy. So at the beginning, your total energy budget here is all kinetic energy, okay? Linear kinetic energy. So all of your energy is this guy right here, okay? So if we want to find our total energy budget at the beginning, in the initial state of this problem, we have to find this for this guy. All of your energy is nothing but kinetic, and that formula is 1/2 mv squared, if you remember. Just talking about it, right? So kinetic energy is that. So if I plug this in, his kinetic energy at the beginning is going to be 1/2 times 49 times his velocity, 3.8 meters per second squared, okay? So if I solve that out, let me get my calculator out here, and I will do this. Okay, so, sorry, I should have had this also brought up before I started the video. And we're waiting. Okay, so we get 0.5 times 49 times 3.8 squared, and you get his total energy budget then for this problem is 353.78 joules, okay? That's all the energy he has to work with. Everything else has to be moved by that amount of energy. That's the energy right there that's going to get everything else in this problem to go. That's our initial amount of energy, so that's the only energy we can have at the end, okay? So what does he do at the end? Well, he jumps on, okay, so at this, he jumps onto a merry-go-round, so he's no longer traveling in a straight line. His velocity, his straight line velocity is now 0. It's not really because it's going to be rotating, but it's going to be continuously changing, okay? So do not worry about straight line velocities, okay? They're gone. What do we have? We have a rotational velocity now. We have an angular velocity. And we want to find out what that velocity is. So how in the heck do we do that? Well, let's first think of what kind of energy do we have at the end. We have something spinning, right? So if you have something spinning, again, it's not at a height, so it doesn't have potential, all right? He's not doing anything at this point. At the end, he's already done whatever he's done. So the work's already been done. You're skipping over that step. So there's no work anymore. It's already been done, okay? And there's no kinetic energy anymore because there's no straight line motion. So the only thing we have left is our rotational kinetic energy is all of our budget now. So that means it has to be this number. That's how much energy we have to work with, okay? So let's go ahead and find out. Let's remember our formula for kinetic energy, rotational kinetic energy, and boom, there it is right there, isn't it? So we know the rotational energy for this thing is 1/2 I omega squared, okay? And we know that the total value for that is 353.78 joules, what we found in the first place, what we found from the last problem we just solved, okay? So what do we do from here? We wanted to find out our omega. That's the piece that we want to find, okay? So we have to find our values for I, and we have to find, well, 1/2 is a number, and we're going to have to do a square root in there to get rid of that, okay? So our I value, well, it's a disk. Maybe I need 1/2 mr squared, right? That's what the I is for a disk. It's 1/2 mr squared. Except, if you remember, in the problem, it actually tells you somewhere, here it is, it tells you what your I value was for the merry-go-round. Now I'm simplifying this problem down a little bit. There's a little bit more to it than this, but I'm not going to have you guys working on this one, okay? So really we're just going to imagine that's what our total I value is at the end, okay? Don't worry about the guy and his, we're just going to consider it to be included. Now is it a cheat? A little bit, yeah, it is. But for starters on this, I think that's a good place to start, okay? So we have an I value already. We don't have to do the 1/2 mr squared because that's already been done for us, okay? So I'm going to erase this down here. Okay, get rid of that. All right, so rotational kinetic energy is 1/2 I omega squared. So 1/2, what was our I value? Our I value was 442 kilogram meter squared. That was our I value that they gave us in the problem. Okay. Now that's also times omega squared, which we don't know our omega, but we know that total value for rotational kinetic energy is equal to 353.78 joules. Okay. So how do we solve for omega now? Well, we have to get it alone. Okay. So that means everything over here, we need to, sorry, that looks more like a 9. Let me clear that up. 442, right? So we need to solve this and then simplify it down. Okay. So 1/2 of 442 is going to be 221 times omega squared is equal to 353.78 joules. Now again, I have to find omega, so I have to try and isolate that thing. So I'll divide both sides by 221. Okay, and what I will find then is that omega squared is going to be equal to, and let me do this again here. All right, so omega squared is going to be 353.78 divided by 221, and we get omega squared is 1.6, basically 1.6008, whatever. Okay, so 1.600, whatever. 1.6 is what our omega squared is. We want to find omega, so we have to take the square root of both sides, okay? So that will simplify this side down. Square root of a square is just the thing inside of it, right? So our omega is going to be square root of 1.6. If you want to know that value, it is, drum roll, 1.27. So that'll get us 1.27 radians per second is our omega. Okay? So that gets you the first problem. I'm going to stop this video and then I'll put number 10 on the next one. Okay? It's already gone